Good afternoon, everyone. Welcome to our last webinar of the year. It's Joanne here from Rockflow Dynamics, and shortly I'll be handing you over to my colleague Olga, who's going to be taking you through today's session. So just to let you all know that your microphone will have been automatically muted. So if you do have any questions, please just pop those into the chat box on your control panel, and we will answer as many of those as we can at the end. After, we'll send out all of the questions and their answers, as well as the video recording for today's webinar in case you miss any of it at all. So now I'll hand you over to Olga. I hope you'll enjoy today's webinar.
Okay, thank you very much, Joanne, for introduction. I hope you will enjoy our small talk and demonstration. So welcome to the Rockflow Dynamics last webinar of the year. It is the 4th webinar, and I'm sure you've probably seen our previous 3 webinars, which we had in 1st, 2nd, and 3rd quarter of this year. So today we will talk about the main developments in tNavigator in 2018 and some of the developments from late 2017. This would be followed by the live demonstration of some of the software functionalities. Okay, some of the key facts of tNavigator as an integrated solution for reservoir engineers and geologists. First of all, tNavigator is a software package developed by the company called Rockflow Dynamics. It is a single executable written in C++ and CUDA languages, and it is designed for modern CPU and GPU processors. This year, we celebrated the 13th anniversary of the software development, and every year we have 4 releases of this product. We have got a team of more than 100 software developers working to advance the product even further. And at the same time, our 45 reservoir engineers in 19 support offices in 14 countries are making sure that our more than 130 clients in 28 countries are getting the best experience with tNavigator. We also support more than 55 universities in 25 countries. Okay, with that, at its 13th year of development, tNavigator has grown to the full Subsurface package, and actually it allows you to complete the full workflow from surface to subsurface. So to begin with, you can build your static model and then dynamic reservoir model. Then you can run dynamic simulations. You can also calculate the PVT properties of fluids, build surface facilities network, calculate lifting tables for that as well, and perform the extended uncertainty analysis. All of these are within one integrated workflow. So there are 4 key development directions tNavigator is following. So the first one is to do with the scalable solutions, parallel solutions for high-speed computations. The second direction is the development of integrated workflows. Then we are always trying to develop some smart usability solutions for the software. And obviously, we are trying to make sure that the advanced physics in reservoir simulations is supported as well. So further in the presentation, I will provide you with some relevant examples of what has been developed in the mentioned categories in the past year. Okay, to begin with is the first development direction, that is actually an area where tNavigator is known to be the market leader. Scalable parallel solutions for high-speed computations. So a little bit of a background here. tNavigator and Rockflow Dynamics as a company always closely following the trends in the computational hardware. So we are making sure that tNavigator is aligned and adjusted to the newest available architectural system to provide our users with the best simulation performance. For this particular reason, way back in 2017, we investigated the possibility of utilizing the power of the graphical processing units, GPU cards, alongside with the classical power of the CPU in a hybrid system. Such hybrid system proved to be working great and showed the decrease in runtime for many models. And initially, we only supported the Pascal series of GPU cards, as they have proved to be the most efficient. But since 1Q 2018, that's what it is highlighted on this slide, we actually introduced a new Volta card, which is now supported by tNavigator as well. And because it is actually demonstrated the decrease of the simulation time even further for many models. Okay, moving on to integrated workflows. So here the RFD development team is building an integrated solutions in one common platform. As I already mentioned earlier, the integrated package includes geological and dynamic modeling, surface, networks, PVT, VFP toolkits, and also uncertainty quantification and optimization package. All of these modules work in common interface, and the links between various parts of the workflow are easy and natural. But the main integration of the year, which I would like to highlight here, was actually the link between the Surface Facilities Builder, Network Designer, and the Subsurface Simulation Model. Currently, what is being done in the industry is that the reservoir models are linked to a surface modeler by the means of a controller. And both surface and subsurface problems are solved independently and sequentially. So us being RFD, we wanted to be able to run these systems implicitly to increase speed. We wanted to be able to plug in our VFP and PVT toolkits into it. And on top of that, we wanted everything to be fast, robust, and obviously useful. That was actually the reason for us to develop the Network Designer and then couple it with the reservoir model, so that the reservoir and surface network equations are solved implicitly in the single system. And obviously, this illuminates the integrator, the controller, which allowing us faster and more stable simulations. So now your integrated workflow can look like the following cycle presented on this slide. So based on your wells completions, you come up with the pressure losses, and they are being taken into account in your Surface Facilities Designer, Network Designer, so that the network production constraints, THPs, are generated for the subsurface simulator to process. And then the subsurface model will generate the well rates, which would be again fed to the VFP toolkit and continue the loop on the next time step. Okay, so tNavigator is also famous for its improved usability solutions. So here, starting from our interactive graphical user interface that allows you to monitor the simulation results at runtime and interact with your model in real time as well. So we have embedded 2D and 3D streamlines, bubble maps, water flood management tools, etc. But what we also do is we're developing a number of features and keywords that allow you to improve model analysis even further and simplify the adjusting model parameters. One of those keywords, actually two keywords, they allow you to introduce a dynamic Algea. This been introduced in the second quarter of 2018 in the 18.2 version of tNavigator. So these keywords, Algea on and Algea off, allow you to activate and deactivate the Algea on demand. For example, if you wish to analyze in more details any thermal effects, condensate banking, water, gas, coning, etc. So those effects which do not happen from the beginning of the lifetime of your reservoir and hence do not require a detailed LGR from the start of simulation. So you can also find various other useful applications for these keywords. Okay, and the last but not least development direction is the advanced physics in reservoir simulations. Here I would like to highlight two big developments which we introduced this year. It's coupled 3D geomechanics and Algea hydraulic fracturing. Starting with the Algea hydraulic fracturing, in the beginning of 2018, we introduced the hydraulic fracture model based on grid refinements and changing of the rock properties in fracture zone, as well as the stimulated rock volume zones, SRV. Such approach allows you to define the fractures of any shape. Your LGR does not have to be parallel or perpendicular to the well. We also allow the logarithmic LGR along the fracture and permeability modification in the stimulated rock volume zones. Another development, this is actually something we are quite excited about, and we find that it is actually pretty unique in the world of reservoir simulation, is the coupled 3D geomechanics. So now we have the ability to solve the finite element elasticity equations along with the fluid flow equations in one system. So this translates into being able to see how your reservoir rock behavior affects the fluid flow and vice versa. So the applications for this could be, first of all, you can localize the potential damage zone within the formation. This could be particularly useful when you're planning the, for example, the open hole well. And if you see a potential damage zone, so we know that this is a red flag and you should probably most likely look somewhere else. Another application is, so we have the extra option called the possible fracture direction, which shows you the potential direction of fracture propagation. Here we're using the fact that fractures occur in the direction perpendicular to the direction of maximum stress. This feature can be helpful when planning hydraulic fracturing, for example. Okay, so this concludes the main development highlights of the past year. And next, I would like to move on to the live demonstration. In the live demonstration, we will show you one of the possible approaches towards the integrated dynamic model adjustments workflow and the results analysis in tNavigator. We will start with opening the existing Blackwell model, assessing its match with the measured historical data. Then we will update its production schedule with the new historical data. Then we will try to adjust some of the model's properties by generating multiple cases and analyzing the results. And then we should have time for questions. Okay, let me now move on to the tNavigator. So you can see the main tNavigator screen. Let me open the existing hydrodynamic model, which I have prepared for this demonstration. File, open as. So here you can actually select the syntax of your model. We support various industry formats here. Okay, that's the model, black oil demo. I press OK. And you can see the screen where with the description of the loading initialization of the model. Once initialized, we can visualize our model structure in 2D, in 3D here. And very conveniently, you can always access the files describing your model from the top menu. For example, so you can see the main file, the data file, and all the include files could be accessed through this menu. So if I click open this data file, you can read through it and understand what is there within the model. Or there's another simpler way. You can just go to this definitions tab and have the quick overview of what this model is, its dimensions, the number of active grid blocks, the model type. So this is a black oil single porosity collector type, the number of wells, etc. Let's go back to the main 3D view of our model. Right, okay, so if we go now to graphs, we can actually see that I haven't even started any simulation, but I already have some graphs, some lines here. This is the historical data, which is introduced in the model through some special keywords, wconhist in this case. So I'm looking at total oil and total water here. Also rates are available on the field level for now. So in order to understand how well the model actually represents this historical data, let's actually run the model. To do that, it's quite simple. Just press this red button called Run. Because I'm visualizing at the moment the dynamic property pressure, you can see the time slider is moving through different time steps defined in your schedule section. So you can actually see which time step we are at the moment. Let me maximize the view. You can actually pause at any time. I pause now just to kind of make some clicks here and to show you that we are actually at the time step 40 at 21st of May 2015. The red bar indicates how much of the results you have in this model. If I go to graphs again and continue running, you see the time slider will just pick up from where we stopped. So looking at the total oil versus total water, you can actually see that we hardly can distinguish between the dotted line, which represents the pressure, which represents, sorry, the measured data, and the solid line, which represents the calculated data. So the model is perfectly matched until 2016. That's great. But I know that we have some additional historical data up to 2018, which we would like to upload into our schedule, and actually see how well the model is matching from there. So if I zoom in actually onto some time steps, I see that we're already starting to have some water production and the match is getting worse. Okay, so you can play with your text file and adjust the scheduler, but that's time consuming and so on. We have the preprocessor tool for that, Model Designer, where you can easily update your schedule. And we can seamlessly access this through this icon on the menu, open in Model Designer. I just press it. So make sure that I stay in the folder where I would like to stay. I will call this new project MD Demo Live, for example. Save it. So now what is happening? The model is being exported to the model designer. Now I just agree that I only need the model designer license. Right. That would be one way to access the model designer. The other way would be just to go to the model designer project and say MD Live, for example. Save. Okay. Let me try again. I'm just waiting for the license. MD S&P. Yes. Okay. So the license been released. So fine. So the other way is just to import the data from existing model. I pick up my data file, open, and say OK. So that's my dynamic model, which you just saw a second ago, but opened up in our preprocessor tool, Model Designer. So the 3D structure looks different. It's because we have the inactive grid blocks activated as well. So let me filter on this ActNum. So I say visualize the ActNum, or the values of ActNum of 1, not 0. Also some other adjustments I would like to do just to cut the well trajectories by depth. Okay, so it's so now I can actually see the name of the well in a better way. Okay, so why we are actually here is to update our historical data. It is easy to do, just to go to the wells data tab in the objects tree. First of all, let's see what we've got imported there already. In the strategies tab, if I expand the development strategy, you can see the list of different time steps from 2014 to 2016. And if I expand any of these time steps, you can see that there are different user keywords. So all those actions, all those keywords describing different actions happening with your well with time. That's what has been imported already. Also in the schedule section, you have a chance to see what are the keywords for all your wells in terms of well definition, in terms of well production. So you see we have lots of WCON hist for different wells, WCON inch for injectors. And then if you don't really know what each of these values represent, just hover the mouse on top of the value and you will see what these numbers actually mean. That is quite handy just to have a look of what you already have in the schedule. Okay, so our next step would be import the additional historical data. I will create a new table. I will call it History 2018. Okay, that's my empty table, which I will populate now by importing the file, which I have pre-prepared at rows. Find the file history to 2018. That's the one. Okay. So in this small preview window, now we need to make sure that each of the column is actually represents the right value, right parameter. So the first column is the well name, the second one is the date. Then we would need the oil rate, that's correct, water rate, then we would need to go to liquid rate. The next one is water injection rate. Water injection. Injection rate. The next one are totals. Oil production, total oil production, total water production. So I have quite a detailed history, as you see here, and also liquid production, and then water injection total. So while I'm scrolling here, you can see what other options could be for you to import. Water injection. Yes, and the last one is the well efficiency factor, which is here. And then I would skip the rest of the columns. Also, we need to make sure that the date format which we are importing is the right one. If not, then we'll just adjust. And the unit settings, we need to make sure that they are correct. Again, if not, then we can adjust here. Okay, that's everything's ready. Press OK. And that's you have a chance to see and to quality check the imported table again in terms of what you have imported. Let me also get rid of the empty columns. Okay, again, just to mention, I've got quite a detailed history here, but for example, if you only have the historical rates, but not the cumulatives, you can just call the appropriate option, calculate, for example, rates from cumulatives or cumulatives from rates, and tNavigator will calculate them for you. That's no problem. Okay, so just scroll down to see that, yes, fine, we have the data until 2018. Going to the strategies. In the development strategy. Now what we need actually to add those additional time steps into our strategy. To do so, I will select the option import include the time steps from the table, and just make sure that it is the appropriate table I am requesting. Okay, close. Right, so now you can see 2015 and then straight away 2018. It's just because the time steps with no rules are not displayed. Let's display all of the time steps. And for the first time step, which has been new time step, which has been imported, let's assign a new rule. What we want to do, we want to create the historical well controls by table. So basically take the historical well controls from the table which we just imported. So again, make sure that it is the right table we are referring to, history 2018. And let's say that the well type will be detected by rate. For the producers, the control mode would be on the liquid rate, and we will agree to the liquid rate, to the historical value of the liquid rate. Then for the water injection, the control mode would be the injection rate, and we will agree to the historical value of the injection rate. Okay, again, good quality check is to go to the schedule section and actually see all operations, for example, and scroll down to make sure that these additional time steps have been taken into account, and actually the keywords have been assigned to them. So wconhist to is here, that's great, and wconinch for injectors. And well on time factor is just taken into account the well efficiency factor which we imported. Okay, perfect. Now we are ready to start to initialize the model. Yes, we are saving the project. That's a good idea. The model is being initialized. So we can see some messages about the process of initialization. And now we can actually start running this model. We see the familiar red button, Run Calculations. Okay. So as you can see, although we are in this preprocessor tool, it also allows us to make changes and do some runs to actually see what these changes are leading to. And obviously for that, for the analysis, we have the graphs here available just to make sure that what we have, that the changes we have done being actually taken into account and they are producing some results. Okay, so here in the graphs, we have some predefined templates. So for example, if we want to look at production rates, so red one is the oil rate, blue is the water rate, and gray one is the gas rate, production totals. In this model, we are actually interested in how our simulation results are compared with the historical. So the some of the useful predefined templates are, for example, history versus calculation. So the dotted line is the history and the solid line is the simulation. Then there's another one, for example, with more plots, oil rates and water rates, then totals, water cut, and liquid rate as well. Okay, so let's make some observations straight away. We can see that there is quite a significant mismatch starting from about early 2016, late 2015. So basically the new history is not matched at all. And our model needs to be reviewed. Okay. So let's actually do some manual adjustments, still staying within the model designer. For example, something which we can notice is that our model is producing actually more water and the water cut is happening faster. Let's say that actually the fastest way is to try to match that is to adjust your relative permeabilities, but we need to have a reason for that, say that we don't really trust our laboratory experiments or this rel perm's been taken from some analog field and it is not 100% correct, etc. But anyway, so tNavigator has some tools which allow you to quite fastly adjust your relative permeabilities. Let's try them. So what we will do, we will create a child model to duplicate this existing model to a child model. And first, we will adjust rel perms, call it dynamic model RP. Okay. There are actually two ways you can adjust the relative permeabilities. The first one is just the tabular one, the manual, and the other one is creating using the approximations, Cori or LET. So let's start with the manual one. We created a new model. It's a good idea to actually leave a comment here just for you to know what this model is about. Adjusting rel perms table. Okay, so that's the comment. So next time you just navigate your mouse to the name of this model, you will see the short description. Okay, so let's go to Fluid Properties tab, expand the relative permeabilities. So here you can see that the existing set of relative permeabilities existing in this model, and it's been set up by the table. What we want to do, we want to adjust these rel perms. What I say duplicate these relative permeabilities. Let's rename it, call adjust. Okay, and I can display them on one graph. Okay, what I will do now, just get rid of capillary pressure curve. If I press the Shift button, I would like to actually slow down my water a little bit. So I would shift my water perm a little bit, kind of making sure that the curve is still fine, even a little bit further, like that. Okay, so now I adjusted my relative permeabilities, and I need to make sure that my new model, which I just generated, is actually using this new set of relative permeabilities. I go to the Fluids tab of my Properties settings and choose the relative permeability adjust. Okay, so now I am ready to initialize the model again. Again, you're familiar already with the procedure. I press this green button, the model is being saved and then initialized. Okay, and let's run the model. Let's go to the graphs. Here on the graphs, same way as in the graphical user interface of the simulator, you have the graphs, but also the numerical values of each graph on the right-hand side, which you can actually, this information you can copy and paste to Excel and work with it if you wish. So let me just close this table just to maximize the view of my graphs. Okay, so now I'm looking at how my model is matching the historical data, and I can actually visualize both of the models, one with the initial set of relative permeabilities and another one using the adjusted relative permeabilities. You can see straight away that in the water cut, for example, I'm matching much better. The blue line represents the adjusted rel perms model. Okay, so that's great. That helped. Another way of adjusting your relative permeabilities, as I mentioned, is to try the approximations, for example, Cori or LET. Let's duplicate the initial model, create a child model, and we'll call it dynamic model Cori. Okay. Again, I go to the fluid properties and I duplicate the initial table set of my relative permeabilities. I will say duplicate, call them underscore Cori, and right click on it and say convert to Cori. Okay, on this display, you see that the solid line is representing the relative permeabilities approximated using the Cori correlations. And the dotted line is the initial set of the relative permeabilities. So we see that the Cori is doing this job great. The approximation is quite good, but we actually want to adjust this approximation. So again, let's, in order to edit the Cori correlated curve, we need to just basically change any of these endpoints in the table. So the easy one, and let's just adjust the shape of the relative permeability of water, and instead of 2.5, let me try 5, for example. Okay, yes, so that's actually what I wanted. I wanted to shift my water rel perm curve down to slow down the water. Okay, if I'm happy with that, I say create Cori keyword. And now I don't have a table anymore, so my rel pumps are defined through query correlations. Again, going back to my case, dynamic model underscore query, and make sure that this time I will assign the relative probabilities query set of rel pumps. Initialize the model, save the project. Okay, great. And now let's run the model. Let's go to the graphs again. And while we are waiting for this model to finish simulation, what I can do, I can actually create my own user template. And here I can set up as many plots on one big plot as I want. Let me do 4. And then populate each window with the parameter which I would like to display. For example, the first one, I would like to see the totals for oil and water. Calculated and historical. The second one, I would like to see, let's say, the rates for oil and water. The third one, let's take the water cut, the simulated and the historical. And the last one, let me look into the, for example, average pressure distribution, field pressure. Okay, so I can call this template, let's call it user template. So this template is saved. Okay, so we can actually now visualize 3 models at the same time. And in terms of the oil production, the model with the relative permeability, with the query correlation, is matching slightly better, I think, than the initial one for sure. Same with the water cut. Okay, so moving on forward, what we can actually, what other analytical tool we can use. So let's use this tool called historical versus calculated. It's a cross plot where you can actually set up what you are looking at on the x-axis in terms of the parameter, calculated parameter, oil total, for example, or we can change it to water rates, totals, and so on. So let's stop with oil total. And on the y-axis is the historical value of this parameter. So oil total calculated versus oil total historical. The dots on the plot represent wells, different wells. So basically, if you want, so if the well is matching the oil total calculated versus the historical oil total perfectly, then obviously this well will fall into this diagonal green line. So if we move the time slider, we can actually see that initially most of the wells were on the green line. And only with time, some of the wells started to fall off the green line. You can actually access the settings for this plot just to see what is what. Also, these 2 red lines is you can set up the threshold just for you to say, okay, if we are within the 10% of the tolerance, then I still consider this match as a good match. For example, up to you, you can change it here. Okay, so let's make some quick observation that there are some wells 35, 50, 48, and 3, which are actually showing the mismatch. And the oil production historical is actually higher than the oil production generated by the model. So staying with these observations, let's have a look where these wells are located on the structure. We can easily create a new filter, call it mismatch, and deselect all. Let's select those wells which were mismatching. It was well 35, 50, 48, and 3. Okay, going to the geometry objects. Let's say look at porosity. Doesn't matter really, just to visualize some property. Okay, so it's a good observation that these wells are not actually spread it all over the field. So they are concentrated in one particular area of our field. So the next thing which I wanted to do based on this observation is just maybe make some adjustments to the permeabilities in all directions just for this area. If I would like to do that, let's create a new property and just easily right click on the properties and say create. Okay, first of all, because I will be introducing these changes to my model, which is Cori, I will duplicate a model from Cori to say POM. I call it POM edit. Any name, whatever you wish. Okay, go back to geometry objects again, and let's continue this procedure. Create. I will create the zone edit and new empty property. Okay, so my next step would be to assign some values to this new property. Let this property be 0 in every grid blocks. Okay, to begin with. And then I will use this quite useful tool, brush config. I will set up the radius of this tool. And what I want to do here, I want to say assign the value of 1 everywhere where in the area where I touch it with my brush, and also apply it to all the layers, to all 128 layers. Okay, adjust the radius even further. So you see I'm just coloring the area which I want to play with. Okay, great. So we created a new property, zone edit. Now using this property, I would like to adjust my permeabilities just in this area. Let me create another property, permx edit. Okay. Right, and let me use my calculator and apply some function to this property. Okay, so if you are familiar with all these if-then functions, etc., that's great, but we have some help for you here. So different functions, max, min, sum, etc., different keywords used for that. I will use if-then function. So the way to use this one, I will say if my property zone edit is equal to 1, so I'm staying within that red area, then I would like to multiply my permeability along x by, say, 2.5. I don't need else if, I will have just one else. Else, I don't want to do anything, just leave my permeability as it was initially. And that's all, apply. So that's my new property, permeability x edit. I can do the same for, I will duplicate this property and call it permy edit. Okay, I will duplicate it again and I will call it perm z edit. You will see why now. So I go to perm y, I open my calculator, and because the perm y been created based on the perm x edit, so the formula which been used to create the perm x edit is saved here. What I want to do is just to adjust, instead of permeability along the x, I would actually like to use the permeability along the y. apply. And the same manner for permeability along Z. So the formula contains perm Y. I will adjust it to perm Z and say apply. Okay, so I created 3 new properties, permeability X, Y, and Z. Now I want to make sure that my new model, which I created, dynamic model query underscore perm edit, is actually using this new permeabilities instead of the old ones. What I will like to do, I will need to assign the new static properties to my model, basic grid properties. Okay, permeability along X would be described by the keyword perm X, but the property should be used is perm X edit. Yes, I want to rewrite an existing property. Then same for permeability along Y. I would like to assign the perm Y edit, overwriting the existing property. And for permeability along Z, I would like to use permeability Z edit, overwriting the existing property. Okay, again, double check that it's all correct. So the keyword will be used perm X, but the property is perm X edit, and so on. Okay, that's perfect. Now let me actually initialize the model again, as we've done before. Okay, initializing. Great, and now I will run the model, and you know what will come next. I will be comparing the results between all of my 4 models, which I looked at today. Meanwhile, the model is running. Some more features which are available here in the preprocessor, same as in the graphical user interface of our simulator module. You have the possibility to visualize your streamlines. So once we are running, we have the pressure distribution of in your model. You can actually see, let me remove the grid. You can see how these streamlines are moving. Oh, sorry. Oh, these are the streamlines. Yes. Right. So you can use the unique well colors for streamlines. Right. Finally. And so what we are looking at the moment, we are looking for the traces from producers. We can change it to visualize the traces of streamlines from injectors to producers. And so on, moving the time slider. At this time step, all the wells are producers. Only at this time step that some of them are turning into injection because I actually have my filtering active. I don't see other wells. So yeah, this is the streamline tool, which many of you who are active tNavigator users are familiar with, but within the preprocessor. Okay, moving back to graphs, let's actually see what sort of match we have obtained. Okay, still a little bit of mismatch in the water cut, but overall in the total production, it's matching quite perfectly. Okay, so I think that's all I wanted to show you. So I just demonstrated you how you can create, edit some new historical data to your existing schedule of your dynamic model. Then you can adjust some parameters and run them different cases within the preprocessor dynamic model designer. And make some conclusions, etc. I've done this manual changes, but you know, tNavigator has the assisted history match module where you can choose the algorithm which will actually optimize the match for you. But this is the other topic. I think the time allows us for some questions.
Yeah, okay, thank you everyone for your attention, and obviously thank you to Olga for the presentation, the workflow. So as I said before, if you do have any questions, please just pop them into the little questions panel on the side of your screen, and Olga will make her way through a couple of those. And we've got a few minutes left, so we'll see if we can answer anything. Have you got anything, Olga?
Okay. Right, so there are some questions. Let me pick up some of them. Right. So the question is, can you link tNavigator to other software? Well, the answer is actually yes. We have clients which are doing that. But what we can actually see more and more frequently, that companies are moving to their fully integrated workflows. So having tried tNavigator and all the functions which we have on offer, they see the huge gain from working inside a single environment and carry out full surface to subsurface studies. Okay. The other question would be related to the hardware. Which hardware do we recommend? So basically, the hardware, so with tNavigator licensing policy, we don't really charge for the amount of for your parallel performance. So the better your hardware is, so the more advantage you will have in running tNavigator. It is a one license per workstation. But maybe we're always looking at the price versus performance aspect, and more or less something like 28 cores, 56 threads, dual Intel CPU with the GTX 1080 GPU card, which will kind of cost you around $8,000, will provide you with a decent performance. Actually, if I look into my screen, so if you see my tNavigator window here, so the GPU card I'm using is actually GeForce GTX 1080, and I have 48 threads, and this shows to be quite an optimal hardware configuration to run many models. Okay, do we have time, Joanne? I think it's 2:59, so we have some more questions. Will all these webinars be available for view later? Yes, of course. So as I mentioned in the beginning, we have already 3 webinars, and this one is the 4th one. All of them are saved. We can provide you with the links, obviously, but basically you can search them on YouTube, RFD webinars, and you will see us there. Right.
Okay, I think,
okay.
Yeah, for anyone who didn't get their questions answered, we will gather all those up and we'll answer them, and then we will send that out to everyone along with the recording of the webinar. And of course, if you do have any additional questions, please don't hesitate to get in touch with any of us and we can answer those for you. Okay, thank you very much everyone for your attention today, and we hope you can join us for more webinars in 2019. Thank you.
Okay, thank you everyone. Goodbye.